Today, we're going to crack the case on a really fundamental question in chemistry. How, exactly, do scientists measure the speed of a chemical reaction? Some reactions, like explosions, are crazy fast. Others, like rusting, take forever. Okay, so our investigation starts with figuring out what we're even looking for. You've got to agree on what reaction speed actually is, and that leads us straight to our first big clue, the rate of reaction. So what is the rate of reaction? Well, think of it like this. It's just how much stuff changes over a certain amount of time. We can either watch how fast our starting ingredients, we call those reactants, disappear, or we can watch how fast the new things we're making, the products, appear. And that's the cool part. It gives us two different ways to tackle this. We can play detective and track the stuff that's vanishing, the reactants, or we can track the new stuff that's showing up, the products. All right, let's get into our first method. For this one, we're going to track a suspect as it literally tries to escape the scene. And in this case, our escaping suspect is a gas. So for our case study, we're going to use a total classic, dropping some marble chips into acid. You know what happens, it fizzes, it bubbles up, and that's because it's producing carbon dioxide gas. That escaping gas is the evidence we're going to track. First, you set up a trap, just a flask connected to a gas syringe. Then you start collecting your evidence. You just record how much gas has been collected at regular intervals, like, say, every 30 seconds. And once you have your data, you plot it on a graph, gas volume versus time. This graph tells you the entire story. The steepness of that line, what a scientist would call the gradient, that is the reaction rate. See how it's super steep right at the start? That's when the reaction is going full throttle, super fast. Then, as the reactants get used up, there's less stuff to bump into each other, so the reaction slows down and the line gets gentler. And then, when it goes totally flat, that's it. Reaction's over. Case closed. On to method number 2. Instead of catching what escapes, this time we're going to measure what's lost from the scene itself. So we're using the exact same reaction, marble chips and acid, but we're changing our technique. This time, we're not going to trap the gas. We're actually going to let it escape from an open flask. And instead, we'll measure how the total mass of the flask and everything in it goes down over time. And the setup for this is, if anything, even simpler. You just place the whole flask right onto a precise electronic balance. You hit the stopwatch and you record the mass every 30 seconds. And because that CO2 gas is bubbling away and leaving, the total mass is going to drop. And then, just like before, we plot the mass against time. And here's what that graph looks like. Yeah, the line is sloping down this time because mass is being lost, but check it out. It's telling the exact same story. The steepest drop is right at the beginning. That's our fastest point. Then, as the reactants get used up, the rate slows, the slope gets less steep, and when it flattens out, the reaction is over. Okay, so we've gathered our evidence using two totally different methods. We've got two graphs that look like opposites. One goes up, one goes down, but they're telling us the exact same thing. So now, let's put it all together. This table just lays it all out perfectly. If you're measuring a product being made, like our gas volume, you get a positive slope, an upward curve. If you're measuring mass being lost, you get a negative slope, a downward curve. But here's the key takeaway. In both cases, a steep slope means a fast reaction, and a flat line, a slope of 0, means the party's over, the reaction is done. We've totally solved the mystery of how to measure a reaction's speed. We know we can track it with gas syringes, with electronic balances, and we know how to read the story those graphs are telling us. But this just opens up an even bigger, more exciting question, doesn't it? What if we wanted to do more than just watch? What if we wanted to actually control that speed? Now that is a question for you to dig into next.